So what I'd like to do in this short video here, you guys, is introduce to you the gas law POGIL activity. And so you guys are going to need the gas law POGIL activity in order to follow along here. What you need to do is come over to Blackboard. In Mr. Gainley's chemistry class, of course, find the properties of gases section over here, and then if you come into the assignments section right here, you will find the gas law POGIL activities. You're ultimately going to need both of them. The gas laws POGIL, this 2015 gas laws POGIL is the one we're going to work on here in today, and then this partial pressure POGIL we'll do down the road somewhere. So go ahead and make sure you have a copy of the gas law POGIL to work on. And so what I want to do is introduce it to you guys, and then I really like to see you work in your POGIL group on this activity a little bit. So I'm not going to go through it in as much detail as I went through previous POGILs with. And let's see if we can do a little POGILing here, see if we can make it work somehow. Okay, so in this activity, what we're trying to do is determine what are known as the gas laws and how to use them. And there's actually 4 different gas laws that you'll use in this POGIL, first half of this POGIL activity. And there's a 5th one that we'll learn in the second half of this POGIL activity, and then a 6th one that we'll learn later on in the week here as well. So what I did was I created 4 models here, and I would have done some demos. Had we done this in class, I would have done some demos for you guys to draw what's happening in Model 2 and Model 3. So I just drew for you. I didn't draw. I think Miss Olson actually drew these, what the activities were in Model 1 and Model 4. So the story's right down here. So Jacob stops at 7-Eleven, buys a bag of chips. Then he hikes up Pikes Peak, and he takes out his chips to eat them. And this is what he saw, right? So when he was at 7-Eleven, here's what the chip bag looked like. And then when he got up on top of Long's Peak, here's what the chip bag looked like. Okay, and so this is sort of the before and after. Now, in model number 2, what I would have done is either, if I was able to bring some in, bring in some liquid nitrogen, and which is liquid nitrogen, for those of you who don't know, is very, very cold. It's almost negative 200 degrees Celsius. Very, very cold. And what we would have done is played with it a little bit, and so you would have seen what making something very cold actually does. If you want to go out and look on YouTube for what happens when you stick a balloon in liquid nitrogen, then you can see this for yourself. But essentially what happens is the balloon that used to look like this now looks like this, right, when you stick it into some liquid nitrogen. So not a bad idea to stop the video here and go out on YouTube and take a quick look at what happens to balloons when you stick them in liquid nitrogen. There's hundreds of videos out there about it. So that's what happens in Model 2. Model 3 was, and I think the actual YouTube site, or the last one that I used anyways, is written right down here for you, so you could jump out and take a look at this if you want. But essentially the question is, what happens to an aerosol can if you heat it up? And so it's a safety video about why you should not heat up an aerosol can, so like a hairspray can or a spray paint can or something like that. But if you go ahead and take a look at that, what you'll see is that your spray paint can starts looking like this. And then after you heat it up a little bit, right, so you add some heat to it here, then the spray paint can explodes, right, and you end up with something that looks like this, right? And so I'm the world's worst artist, as you can probably tell, but you get the basic idea. A good reason, a good safety tip, don't ever heat up a spray paint can or an aerosol can of any kind for that matter. And then in Model 4, Ms. Whitsitt gives Jacob a weather balloon ride for his birthday, and so gives them a weather balloon, not a weather balloon ride. And then the weather balloon, of course, is released into the atmosphere, and then it goes way up high, up into the stratosphere. And what happens is the balloon actually gets bigger, 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 bigger as it goes up. So those are our four models, and what we're going to do is try and understand, according to kinetic molecular theory, why what's happening is happening, and then describe a relationship between two of our variables, right? Our variables being pressure, volume, temperature, and number of moles, as we've been talking about here. Okay, so I'm going to do the first one with you guys here, and then I'm going to ask you guys to sort of finish up the first half of it on your own. So here's the four laws that we'll be dealing with here: Boyle's law, Charles' law, Gay-Lussac's law, and the combined gas law. And notice the variables are shown in here. So Boyle's law is a relationship between pressure and volume. So the ones mean the initial pressure and the initial volume, and the twos mean the final pressure and the final volume. Charles' law turns out to be a relationship between volume and temperature. Gay-Lussac's law turns out to be a relationship between pressure and temperature. And then the combined gas law actually combines all three of those laws. So these first four laws we're going to learn about are pressure, volume, temperature relationships. So nothing having to do with moles yet. So let's do the first 3 or 4 questions together here. So we'll do the very first model together, and then you guys will have an example, and then you can do the other 3. So in our first model here, it's is the one where we took the chips from whatever altitude we were at up to a higher altitude, and looks to me like the gas container got bigger, is what it looks like to me, just looking at these 2 pictures, which means the volume changed. And so in model 1, which 2 variables are changing? Well, one of them that changed for sure is the volume. Now, whether you know this or not, before you started this POGIL, you will definitely be using it from here on forward, which is, I think we talked about it initially when we talked about atmospheric pressure. As you go up in altitude, so we went from where we are here today at about 5,000 feet in altitude up to the top of Pikes Peak, which is over 14,000 feet. So we went way up in altitude. And when you do that, you guys, the atmospheric pressure decreases dramatically. So the pressure that was pushing down from the outside on that bag of chips got smaller, 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 smaller. So to answer question number 1, in model number 1, which 2 variables changed? Well, volume changed and pressure changed. Now, you could argue that temperature changed also, and I think it would be a valid argument, but I just want you, in these cases, just to choose the 2 main variables that are changing. So pressure for sure changed and volume for sure changed. Okay. In model 1, which 2 variables were remaining constant? Well, temperature, we're saying, didn't change, even though you could argue that it might have. And definitely moles did not change. So there was no added gas or subtracted gas. So temperature and moles did not change. Okay, based on which variables are changing, which of the equations best represents the situation in model 1? Well, it's a relationship between pressure and volume. So it's got to be this law right here, right? A relationship between pressure and volume. Temperature didn't change, right? So it can't be Charles' law, can't be Gay-Lussac's law, can't be the combined gas law. So it's got to be Boyle's law. Okay, so this one here is definitely Boyle's law. And then explained what happened to Jacob's chips in terms of the changing 2 variables. Well, we know that the volume went up. And why did the volume go up? Well, the volume went up because the other change that was happening was, as we stated, as we went up in altitude, the pressure goes down. So here's my container here, and the atmospheric pressure that's pushing on that container decreased. And so if the atmospheric pressure decreased, then what happened is the container got bigger. Okay, the container got bigger. So what happened to Jacob's chips in terms of the 2 changing variables? Pressure went down and volume went up as a result. So what you're going to find in any of these gaseous systems is if one of the variables changes, then another one's going to change in order to compensate for that. Okay? So there we go. There's Model 1. And then what I want you guys to do is go ahead and take a look at Model 2. So go ahead and answer questions 5, 6, 7, and 8. And then go ahead and take a look at Model 3 and answer questions 9, 10, 11, and 12. And then go ahead and take a look at Model 4. And then go ahead and answer questions 13, 14, 15, and 16. And then, oh, here's our stop sign. And I want you guys to stop right there, okay, after you answer number 16. And then we'll talk about it in class the next day and make sure that everybody sort of got the idea here of how to do that. Okay, short video for today. I'd really like you guys, like I said, to work with your POGIL groups on this if at all possible. All right, talk to you guys soon.